Okay, welcome everyone to my continuation of what are my favorite theorems. A very biased collection as usual. Today not really a theorem. There will be a theorem, but not really a theorem, but more like a philosophy or a new part of mathematics, which is called homotopy type theory. So homotopy type theory is homotopy plus homotopy plus type theory. So plus type theory. And I was hesitating to make this video for a long time because it's actually pretty difficult to explain. So, and I probably will end up with mostly waffle in this video. And I was a little bit worried about that. But then I realized that essentially all videos I'm making are waffle anyway. So that probably doesn't matter so much. And why is it so difficult to explain is because it's a mixture between two fields, a really brilliant mixture between two fields, namely homotopy and type theory, that look very different. So I can't assume that you know what homotopy and type theory are. If you do, then it's actually not so difficult. But if you don't, bear with me. I'm trying to make the point here of mixing two fields, which are kind of very different. And it's very interesting. So I will call homotopy type theory hot, if you want, during this video, because essentially pure mass in general, so if you look worldwide, on average, is suffering a lot. So a lot of money is running into other fields. That's fine. Science is always part of a trend, right? So everything, some things are trendy, some things are not trendy, some things get money, other things don't get money. So in general, pure mass is suffering quite a bit. And in some sense, the purer your mass is, the more it is actually suffering. But this one is not. It's actually quite growing, and it's part of logic. So that's kind of a surprising thing in some sense. And it's related to that it is actually pretty beautiful and powerful. So my main theorem will show you that kind of it's an application, if you want, and will kind of show that this is a very powerful idea. I should have said here that I was counting logic as part of mathematics. That's a bit questionable, but I will just go for it. Because the difference for this video, whether it's part of mathematics, whether mathematics is part of logic, or whether I just run in parallel and there's some intersection, that doesn't really make any difference here. Anyway, so homotopy type theory is hot in many senses of the word. And how old is it? It's roughly from the 90s. It depends a bit how you count the start. So it's a fairly new field of mathematics or logic, whatever you want. And it's a mixture between two ideas. First idea is the idea of homotopy, or HO in this video. And this works as follows. So homotopy is essentially the idea of identifying spaces up to continuous deformation. So here's my main example. So take the plane with a puncture. So there's a little hole in the plane. So what I can do is I can put my finger into that hole and then stretch out the hole so that the point gets much bigger. And at the same time, I can grab the plane at infinity, if you want, and pull it inwards. And that operation shows that this space is homotopy equivalent. So what I just did is called a homotopy. It's homotopy equivalent to a circle. So it's kind of a really strange notion. For example, it destroyed here the dimension. The dimension here was 2, and the circle is clearly not of dimension 2. So homotopy is a slightly weirdish operation. Here are some more examples. So you can collapse the thick letter A to its kind of skeleton, and similarly you can collapse the thick letter C to its skeleton, and you could collapse the skeleton further of C by just taking both ends and squeezing them together. So this is actually just a point. So very destructive from dimension 2 to dimension 1 to dimension 0. So this little symbol here is homotopy equivalence. So it's absolutely not clear why that should be a good notion if you see it for the first time, and only history proved that it actually is a good notion. So let's say the idea of homotopy goes back to Poincaré, like 120 years ago, and Poincaré was studying geometric topology mostly, and this was not the point, right? So homotopy was too destructive, and actually what Poincaré really wanted was something like homeomorphism, which is a type of the same type of operation, but not as destructive. But later it turned out that homotopies are the main concepts of algebraic topology. It's really the correct notion of equivalence in algebraic topology. So homotopy type theory will kind of mix algebraic topology with type theory. And kind of the main idea will be to replace whatever logic operations by homotopies. And I will be a little bit more precise later on. I hope this picture is clear. It's kind of an equivalence on spaces where you can just stretch and compress things up to a certain point. I'm not going to write down the formal definition. So here, for example, this space, the sixth thing you see in the middle, whatever, like this figure 8 here, that's homotopy equivalent to the outside, so which would be just the disk with 2 holes, by following the lines by just pulling it in, by pulling out, by squeezing in the outside and by pulling out the inside. So that's the idea of homotopy. And the point I want to make is that's the right notion underlying algebraic topology. Not geometric topology, but algebraic topology. And on the other hand, in the other corner, we have type theory. So what is type theory? Well, it originates something like 110 years ago or 120 years ago in work of Russell and Whitehead, trying to avoid the classical paradoxon in set theory that a set could be an element of itself. Very strange thing. You don't want that. That always leads to problems. And the idea is to just give things different types. So let's say this is type 1 and this is type 2. Then type 1 can sit happily in type 2, but type 2 can't sit in type 2, so you avoid this little paradox here. And if you are into computer science, and I'm a lot into computer science and programming and all that related stuff, then this is exactly what motivated data types, if you want. So if you're programming in a language, and you sometimes depends on the language and you're not careful and you see the letter 5 and just think, oh, that's an integer, it's a number 5, right? So 5 is certainly an integer. So I can apply my integer operations that I know, modular division or something, to my number 5. And then the compiler tells you, no, this is not an integer because you told me in the very beginning that this is some other type, whatever, a cyclotomic integer or something. So it distinguishes the types of objects. And that is very annoying if you see it in the first time. And you always somehow get it wrong, and I still get it wrong. But it's kind of very important because eventually it avoids, or it helps you to avoid mistakes in programming, and then in general in logic itself. Having types floating around avoids or forces you to avoid mistakes, which is absolutely great. With again, like with the programming language, slight problem, if you want, that is kind of really difficult if you see it for the first time and you somewhat always get it wrong. It's kind of a very complicated formulation if you really see it for the first time. So those two have something in common. So this one is slightly strange from the viewpoint of geometric topology, so from kind of the more natural viewpoint. And this one is slightly complicated for the formulation of set theory itself. That's why you probably won't see it in your study of set theory. But it's actually, both of them are useful. One of them turns out to be useful via algebraic topology, and this one turns out to be useful via computer science. Essentially, having types around kind of forces you to avoid mistakes. And homotopy type theory just mixes those two ideas, which is absolutely brilliant because they look completely unrelated. So essentially, you interpret type theory using homotopy, and your types are now spaces called homotopy types, and you can play topology games on your types. So logical constructions become homotopy invariants, and functions become homotopy functions, and so on and so on. So you can manipulate types as spaces, which is the whole point of this language. And it's really kind of great. So you can, like you have an operation in topology, like you have this little loop here, and you can project it, it's living in a torus, and you can project it down to a more standard loop. And there's something similar in type theory, where the torus is a certain type, and the loop is a certain type, and you can project them in a certain way, and this is absolutely great. So you can play homotopy games, topological games on types, on logical objects, which is fabulous. Just think of types as, again, in the computer language, and now you apply homotopies to it. This is absolutely great, a very fantastic kind of idea. It's not trivial that this actually works out, and there was a lot of work. People try to make it work, and it works really well now. I think this is absolutely great. Kind of a very non-straightforward idea to merge those two concepts. And I promised you a theorem, so here's the theorem. So in homotopy type theory, I told you that types are spaces, and you can actually have a space which is a sphere. Right? So the sphere makes sense as a type. And you can define homotopy groups of types. And then you can ask, what are those? And you can prove the classical statement, which is now a statement in homotopy type theory. It's about types. It's a statement in logic that the fundamental, so the homotopy group of the sphere, the nth homotopy group of the n sphere, is exactly the integers, which is this diagonal here in this picture where you can always see this was a really bad diagonal. Let me try again. So if you follow here the number z's, that's a diagonal where the statement is true. A very classical thing in homotopy theory. And this really gives you a new proof of classical statements in homotopy theory. And that's already quite cool. So you have new methods of proof in homotopy theory using computer science ideas, if you want. But the real upshot, and this is why I like this so much, and I've chosen this for kind of the theorem of this video, the real upshot is that now this thing here, because it kind of lives automatically in computer science, you can kind of take the proof, formalize it in a proof assistance, and you get a computer verifiable proof, which means that this statement in classical homotopy type theory has now a computer verified proof. And it is not clear how to do that with a classical proof in any form, but for this proof, it actually can be done. And it's pretty great. And this is kind of the big hope that I have here on homotopy type theory, which is lacking a little bit of applications. But this one is an absolutely great application. So there might be a way to kind of formalize all of homotopy theory in proof verification, or even better, to have the computer write proofs itself. So not just verifying proofs, but let the computer write proofs. And I think that that's a really an absolutely fabulous application of homotopy type theory. Right? So you can potentially prove all of classical topology with the computer, which is absolutely great. It's absolutely a fabulous application. And it really comes from the fact that now types are spaces, and you can mimic the operation on spaces on types, but types are way closer to computer science than spaces, so you can kind of bridge everything nicely together. Anyway, so let me at least give you a hint where the power of, or at least in my opinion, where the power of homotopy type theory comes from. So in homotopy type theory, you can think of a type, if you want, as paths, or of objects as paths. So here A and B, they're clearly not the same, but they are homotopic. And homotopic for this picture just means you can put a surface in between them. Right? That's a way weaker notion than being the same. I can draw another homotopic one. Here's another homotopic one. I can put another surface in between, and so on. So homotopy type theory replaces equality by something weaker, namely by homotopy. In this case, you can put a surface in between. And inequality becomes just a path in the space, and you can play topology games on logical equations, not just the other way around as we did here, where we played computer games on topology. And now we can also, of course, also can play topology games on computer stuff if you want, which I think is absolutely fabulous. Anyway, I hope you enjoyed this video. This is a big waffle, and I also hope to see you next time.